Let's finish up the recursion with another one with a lot more branching than we have seen before. Here is an interesting problem of a chessboard knight's tour. So starting from any given square, the task is to use a chess knight and the jumping L moves as demonstrated in the animation to find a path that visits every square exactly once. Okay, this one didn't create a cyclic tour, but this way we have to generate this kind of a sequence of moves. So notice how from when your horse is on a square, so then it can jump into potentially 8 different directions. So we get so much branching that it's better to do it with the loop inside the recursion. So recursion and loops can be combined. So you use whatever tool from your Swiss Army knife is appropriate for the current task. So this knight's tour, there's a couple of other good recursion things illustrated. So first of all, so the parameters, how big a chessboard and the coordinates of the starting square. And now in this we're not gonna make the knight tour itself recursive, but we're gonna be defining a recursive utility function inside the function. We haven't done this before, but remember, functions are objects like any other objects, and your names are referring to them. So if you accept the fact that you can define a name and assign it to a list or a string or some other object, so shouldn't have too difficult to accepting the fact that you can define a name and associate it to the function object in the namespace of the current function call. So we can make a recursive function inside the function that is not itself recursive. And when a function is inside another function, it can see all these other names in the function's namespace. So basically the function's namespace behaves like the global namespace for just the functions defined inside the script. So a result, so the answer that we're building up, the previous example we were returning it, but here we have it on the side, so then the recursion fills in the result when it finds a solution. And the knight's tour, so this is now very important that we can efficiently tell which squares the path has already visited. So if only there was a mechanism that we could add and remove things and quickly tell us if it already contains something. So of course that's gonna be the set. So the set of the squares that already been visited. And then, so here is another good technique. So we need a for loop that from the given knight position calculates the possible moves. So we're gonna make a tuple consisting of the possible move offset. So that these are the 8 possible ways to make a L move. So 2 steps to the right and 1 down, or 1 step to the right and 2 down, and then all the possible combos, so negative values for 8 different directions. So then we can just loop through this offset list and then use that to calculate each position inside the loop. Okay, utility functions. Notice you can make function inside the function. So this operation testing whether we are still inside the chessboard. So let's extract as a separate operator of its own. So we're using one-based indexing. So both x and y have to be greater than 0 and at the same time at most n. So notice and, so all have to be true at the same time. So now we can make a function as all the unvisited neighbors. So if your knight is currently at the square xy, so what is the coordinates of all the neighbors that haven't been visited yet? So now the list comprehension here. I guess we could also use the lazy version, but this is nice enough here. So the list comprehension. For every possible direction offset, so delta x, delta y, so 2 to the right and so on. So then that is in the move sequence. So the current position coordinates offset by the dx and dy, but only if this other move is inside the board and is not in the visited moves already. So notice the function can see the names inside the surrounding function. So this visited, whenever we construct a tour, we always add and remove the squares in it to keep track of the state. So list comprehension, this one is a happy thing. So we get automatically the list of all the unvisited neighbors. So having all these utilities, so the recursion here, this now very much resembles the subset sum recursion, but in the subset sum there was two possible branches, so we could just handle them with just the code itself, but as the expression goes, so 3 or more use a for, and now we can have up to 8, so we're gonna be using a for loop to loop through all the neighbors of the current square. So the problem, when you're standing at the current square CXCY, generate the rest of the tour. So where the current cell, the current square is appended to the result list. So result list, when the tour completes, we can read the answer from there. And the base case, so every recursion must start with the base case. If the result is now a complete tour, so it contains all the squares, we know that there is n by n, so we know this. And then, so one last hurdle, so the entire chessboard has been visited, but to be considered a closed tour, so it must be possible to jump from the current square to the starting square. So now so a clever way to do this as a one line. So is the direction offset between the two squares one that is a possible knight's move. So the knight's move, this list contained them all. So then this is something that is either true or false, so we return true or false. So notice this function returns a truth value telling whether the solution was successful, and then in the case that there is a solution, then the solution can be read from this outer result. Now where were we? So the base case is complete tour, and then add to the set of the visited squares. Again, there is no law having the exact same data in two different data structures. We have it in the result list and the visited set, because visited set gives us the quick membership, and result then tells us the actual ordering of the squares. If you were given a knight's tour but it was scrambled, so then it's just a random permutation of chessboard contents, no information. So the ordering information that is inherent in the result list is very valuable for us. Okay, so now your task, continue the tour from the current. So now, so loop through all the neighbors, or that all the remaining open neighbors one knight's move away, and then recursively for each one, so try to generate the tour from that starting from that place. So if that succeeds, so this is now this when you're looking for one solution, so the moment that you get the good news that there is a solution, so then you drop everything and just say deliver the good news back to your own caller. So then so we're not gonna undo the current move here, because remember the result, we wanna maintain it once somebody finds a solution. Otherwise, so the same principle that we saw in the subset sum, that the way that you modify your data structures before the recursive calls, then you undo the modification. So we pop the last from the result and from the set of the visited, so then we remove the current square, and then return false. This is the failure, that we tried all these neighbors and all the possible ways from them to complete the tour, and they all failed, and therefore it's impossible to complete the tour from the current state. So this, I guess there should be extra space in there. So then the actual function that wasn't recursive makes the top level recursive call for the inner recursion, and takes the result, and then so here we're turning the truth value, that if this returns true, we're gonna return a list, and otherwise we're gonna be returning none. So the knight's move problem, knight's tour problem, so Wikipedia page explains it, and running the knight's tour for various values of n. So 2, 3, and 4 have no solutions at all for a Knight's Tour. 5 has one, so we're looking for one solution, so here is one solution, and for a 6 we have a solution, and the 7 looks like it's getting harder. There's the number of possibilities grows humongo exponential, whatever is the correct term. So this is the exponentials for you, so we're hitting the inflection point, so the number of possibilities, it just multiplies in exponential rate. So something like so if you wanna calculate the tour for a 20 by 20 board, so then you're gonna be needing a lot more clever techniques.